Hello and welcome back to algebra. Calculus 2. Calculus 2, section 10.7. This is our second part for ratio test, one of the most important tests. It is another one of those unique tests that you can pretty much always tell when you have to use ratio test, because it is used for series which will have different types of functions involved. It will vary, in my opinion, it's very easy to spot when you are supposed to use one of these, but let's test and see what is going on here. So the proposition for ratio test is pretty much the same as the conclusions are the same like for the root test. We just have to work with a proposition for it. So let's say like this: let summation an be an infinite series. Right, you have the infinity right there. And you have a limit as n goes to infinity of an plus 1 divided by an in absolute values. Those absolute values are not there for decoration. You must have them. And we will really specify that in the chapter 11, right? Well, that's in 2 days. So we really have to have these. All right, so now when you do this limit, you will get one of the three possible answers, and those are exactly the same as before. You can get answer less than 1, which will give you convergence, more than 1 or equal to 1, more than 1, which is divergence, and equal to 1 test is inconclusive. So ratio test will ask you to find a limit of a ratio of the next term divided by the current term, and that will give you something. All right, so let's take a look at a couple of good note over here. Note, if we have factorials, we use ratio test. Note squared. If we mix different functions, we use ratio test. Note cubed. Power series, chapter 11, we'll use ratio test. So yeah, get on board, right? Let's take a look at a few of these. So we always divide the next term, which is an plus 1, by an, and an is what's given to you in the problem. So say you have a good old geometric series test from 0 to infinity. Let's say you have 1/3 to the n. I'll just put in parentheses, we know that series converges by geometric, right? But we can also do the ratio test here and figure it out. See, your an is 1 over 3 to the n. Your an plus 1 is 1 over 3 to the n plus 1. So your limit, when n goes to infinity, of 1/3 to the n plus 1 divided by 1/3 to the n is actually, when you use algebra to peel off 1/3, I forgot these absolute values. Holy nightmare, it's a bad day. There we go. Hey, easy. These cancel. And we get 1/3. It's less than 1. Converges by ratio. So, good old problem that we know, to solve using geometric series, ratio can do it. So, technically, we don't need geometric series anymore. Yeah, we do, because ratio test actually doesn't tell you what it converges to. Geometric series has that formula with S, if you remember. A divided by 1 minus R, right? You can calculate the sum using geometric series. Ratio cannot give you the sum. But if you just need converge, diverge, yep, ratio is good. What else can we eliminate? Remember how divergence test says that if you have the derivative to be different than 0, you'll have divergence, right? You can take the limit as well using the ratio test. You will get the same. Let's take a look at some of these other examples with the factorial. So the book has 10 to the n factorial. They have k's. I'm just going to use n's. Okay. Remember how the note 2 says if we mix different functions, we use ratio? Well, this one over here is exponential. This over here is factorial. Also, note number 1 says if you see factorial, use ratio test. Awesome. All right, so what do I need in this case? Well, we know that our an is 10 to the n over n factorial. We know that our n plus 1 is 10 to the n plus 1 over n plus 1, everything factorial. Stuff all of that into limit. Don't forget the absolute values. So you have your 10 to the n over, 10 to the n plus 1 over n plus 1 factorial divided by 10 to the n over n factorial. I just taught this today in my algebra class. If you don't know how to deal with the division of fractions, of rational expressions, go check that out. What I'm going to do is I'm going to peel off a 10 to the n divided by n plus 1 times n factorial when I peeled one off, times n factorial over 10 to the n, right? We have to flip this one into multiplication. Those of you that are still unsure what's going on with factorials, I'll just put this on a side. N factorial is 1 times 2 times 3 times times n minus 1 times, and it ends with n. So this has to match the last integer of the sequence you are multiplying. Has to match it. So what is your n plus 1 factorial then? Well, it's 1 times 2 times 3 times n plus 1. Because these two have to be the same. So it ends with n plus 1. So now, if you understand that this over here is n factorial, and then you still have n plus 1 to multiply it by, and that's equal to n plus 1 factorial, that's how I got this. n plus 1 factorial is you peel off the last number, and then you have all of the previous numbers buried within n factorial. So when you cancel a whole bunch of stuff, this kills that, this kills that, then you are going to have to deal with the limit n goes to infinity of 10 over n plus 1. Now, since n is positive and so on, we actually don't need absolute values now, because all of these values are positive, and this is 0, which is less than 1, which is convergence. Convergence. All right. What else do they have? So ratio test is very easy if you're able to do algebra, right? It's a joke. You just have to divide using algebra, cancel a whole bunch of stuff, and then that's it. All right, we have alternating series now, and this, just by looking at this, because you have the divergence test, you should know that it diverges, because you have we had that lecture where we learned which function grows faster, right, than which, and we learned that this is the boss, the fastest growing function, and this is the one underneath. So if you have fast over slow, it's infinity, i.e. limit is not 0, has to diverge. But let's say you know nothing of that, and you want to, do this. Well, an is going to be, why did I put k? It's n. N factorial. There we go. Now note that I avoided writing this one. I have two excuses for that. Excuse number one is I'm going to stick all of this in the absolute value. So I can just drop it now because absolute value will kill it. That's the major excuse. The other excuse was, do you remember when you learned, hopefully you did, alternating series? Remember that an did not contain -1 to the n? So that's excuse number 2. So you have two excuses, and I hope they're good enough for you. Okay, make a n plus 1. That's going to be n plus 1 to the n plus 1 over n plus 1 factorial. Limit n goes to infinity. Absolute value is the one that would kill both of -1 to the n and -1 to the n plus 1, so we don't have to worry about those. I have n to the, no, I have n plus 1 raised to the n plus 1 divided by n plus 1 factorial divided by n to the n over n factorial. That's it. Limit n goes to infinity, and let's get busy. So I get to write this one here as when we can drop the absolute values, but whatever. I have the n plus 1, right? Because I have plus 1, that's going to be n plus 1 times n plus 1 to the n divided by n plus 1 factors out, and then I have n factorial. That's this one. You see the orange formula on top of the screen now. Times the flip of the bottom, n factorial over n to the n. Cancel, kill, and yeah, there we go. We are left with the limit n goes to infinity of n plus 1 over n, everything to the n. Well, if you do the division inside, you get 1 plus 1 over n to the n. I asked you to learn this one, so we don't have to go through the calculation. So I'm hoping to see everyone in the chat. We have about, 12,000 people watching. It's nice. So many of you like Calculus2. I would like to see at least 10,000 of you write what the answer for this limit is, because you're supposed to know this by heart, right? Someone shakes you out of bed at 4:15 a.m., ask you this limit, you should just say, let's go. Don't be shy. I guess you guys are still asleep, right? E, which is bigger than 1, which is divergent, and we knew that before we even started the problem that it's divergent, because it's a fast over slow in terms of the functions. Memorize this limit. It's one of the calculus major results, which is going to be back time and time again. What do we have? I guess we can pick something from homework and call it a day, huh? For this, then we're going to work on 10.8 to finish the chapter. So let's take a look at a problem. So. Let's do a problem that has factorials, because that's what you have the problems with. So let's start with 37. Summation n goes from 1 to infinity, n to 100 divided by n plus 1 factorial. Gut feeling is convergence, because this is a polynomial and this is factorial, grows much faster. But let's see. My an is n to 100 divided by n plus 1 factorial. My an plus 1 is n plus 1 to 100 divided by n plus 2 factorial. Ratio test, because it's factorial, it's mixing also two different types of functions, right? So we use ratio, which is the limit. N goes to infinity, must put the absolute value there. And we have n plus 1 to 100 divided by n plus 2 factorial divided by n to 100 divided by n plus 1 factorial. Alright, so this is a limit n goes to infinity. We have to write this limit in every step until we get to use it in the last step. And what do I have? Well, I have n plus 1 to 100. Nothing I can do there. Unless you want to FOIL this. Divided by, I'm going to peel off n plus 2 and just leave n plus 1 factorial in there. So I just peel off one term times n plus 1 factorial divided by n to 100. So now we cancel what we can, and in this case just the factorial dies, and I am left with the limit of n plus 100, sorry, n plus 1 over n to 100 times 1 over n plus 2. As n goes to infinity. So the limit of the first one is 1, because they have the same powers, times the limit of the second one is 0, and we get 0, which is less than 1, which is convergence by ratio test. It is just algebra, and then you take the limit from chapter 2, from Calc 1. That's your life. Now let's take a look at problem 35. Has a little bit of this factorial black magic in here. Let's see. We have 2n plus 1 factorial divided by n factorial. I hate that the book is using k's. The reason why I don't like it is because I learned it with n's, and I taught 10 years with n's, and then the addition of the textbook in the last, 3-4 years to start using k, and I'm just like, no, after, years of n's, it's just so hard to switch. So I'm reading all the problems as k's, I'm writing them as n's. You can use whatever, you can use m, you can use l, right? Any of those discrete counters, lowercase I, even though could be confused with complex I, but computer science uses I as a counter, right? You row I++, right? To increase by 1 in Java. So let's go. What do I do in this case? Well, I write my... So it's going to be algebra, and you have to be very careful, right? So it's an is just what we have. You Control C, Control V, right? That's what we do. Now an plus 1 is interesting. I'm going to give it a new line because I have to compute this thing. This is 2 times n plus 1 factorial, and then n plus 1 factorial squared. So I have to do some magic here, right? So what do I have up there? I actually have 2n plus 3 factorial divided by n plus 1 and then n factorial. And then each one of these is getting its own square, because in algebra, when we have a, b, everything squared, you get your a squared and your b squared, right? That's the power rule from algebra. So when I break this into n plus 1 times n factorial, because everything was squared, each one gets their own squared as a power. So where do you usually trip? You trip on this stuff, right? You know calculus, you know limits, you know integration, you can do partial fraction decomposition and all of these crazy things, but then you can't deal with a square. So limit n goes to infinity, absolute value. I have my 2n plus 3 factorial divided by n plus 1 squared times n factorial squared, and I'm immediately going to just flip the other one, skipping steps over here because boss, okay? There we go. Nothing else exists in the world right now. All I need to do is to solve this, where I already see that I can kill these off, right? I just need to deal with those factorials and I am good to go, right? Limit n goes to infinity. These absolute values can be dropped now, but yeah, what the hell. All right, so see, this is 2n plus 3. So 2n plus 3 gets kicked out, 2n plus 2 gets kicked out, and then 2n plus 1, I'm going to leave that as a factorial because that will be canceling with my 2n plus 1 factorial that it's already on the bottom. So now when those two die, there we go, I am left with, and all of these n's are positive, right, because n starts at 0 or 1 or somewhere and goes to infinity, so we can drop absolute values as well. Limit n goes to infinity. I have this 2n plus 3 times 2n plus 2 divided by n plus 1 squared. And the limit of that is 4. Because if you take a look at the highest powers, that's 2n times 2n is 4n squared, and the bottom has n squared. Well, 4n squared divided by n squared is 4. So that's bigger than 1 and diverges by ratio test. Diverges by ratio test. Cool. So that's the ratio test. Again, you are going to see this, well, obviously in 10.8, which is next section, coming up in 5 minutes. But you're also going to see this stuff in chapter 11 and then differential equations. So make sure that the ratio test is strong, right? Make sure you know it well. I'll be back in less than 5 minutes for 10.8, which is one of those survey sections where we decide what is the appropriate test to be used to solve problems. So I'll be back quickly, don't go anywhere.